Welcome, everyone. We survived 1 week. That's good. So we are going to get started in a moment. Just give a couple more minutes for people to join in. Hopefully, so far you've been enjoying the class. The pace, I think, is good so far. I got different kinds of feedback from different people, and I understand that in a large seminar like this, there will be people with different backgrounds, with different knowledge base. So it might feel for some a recap, for others it may be something totally new. So I just want to get everybody on the same base in the first week. So that's been accomplished more or less. And then from here on, we'll be picking up the pace a bit and then going into some advanced models and other fun stuff. So let's see. Somebody's asking how many attendees are there. So right now we have about 200 people signed in right now. So that's a pretty good size. And hopefully people keep joining in. And if you're not able to, or if you're busy with work or something else, you can always go back to the YouTube channel and watch the lecture there. So we'll do our best to put this out as soon as possible. And let's get started right away. So this is lecture number 4. And we are running a little bit behind, but we'll catch up. So it's not a problem. I just want to make sure that you have a good fundamental understanding of what is going on intuitively. And then we'll have some theory, and then we'll build some engineering around it with tools and TensorFlow so that you're able to solve these problems. So let's see what we can do today. We are going to do some recap. We're going to finish up with the maximum likelihood estimation, build an autoencoder, and then build a pipeline to see how we can deal with large data sets, how we can read images, how we can batch inputs. So that's going to be something that is important for dealing with real data sets. So far we've been dealing with toy data sets. They're small, we can read them, build networks that we can solve in real time. But once you are dealing with real data, you will be handling large amounts of data. They may be large and big, and then you may want to understand how to build pipelines for data sets that is more efficient. So we'll cover that as well. So before we get into that, let me answer some questions that came in last time. Again, I tried to answer questions as they come along, but sometimes it may take up the whole class just to answer the questions. So I pick a few questions that are kind of representative of all the questions that came in. So hopefully those will answer most of your questions. So first one, I put names here for the people who asked them. I just want to give them credit as well. So can too many layers be harmful? So obviously, if you have more layers, you are going to increase your time to train and then increase the use of your memory. So that's obvious, but then can also be harmful in other ways. So the answer is yes, because if you don't have enough data and if you have too many nodes in your network, then you're not training efficiently enough. Also, there is a danger of overtraining, and which means your network may memorize. So each of those nodes can kind of understand each of the data points and memorize your data set. So you want to avoid that as well. So that is another harm that can come from having too many layers. So basically, if you have too many layers, you have too many nodes, and that follows from that. So in the sine curve case, would it be good to overtrain? So in general, it's never good to overtrain. So once you overtrain, it means that you have memorized the data and you're not able to predict properly. So you don't want to overtrain ever. Third question, can you include the periodicity of the sine wave in the model? So that's a good question. So in our case, we are only predicting within the input data range. So when you do regression of the kind that we did, you can only predict within the data set. You can extrapolate somewhat, but not a whole lot. So to understand the periodicity of the sine wave, you may want to understand it on a basis of a time series. So which means you need data that is time-based. You need data from multiple time points. So there are other kinds of networks that are used to solve these, and we'll go over them a little bit. And these things are called recurrent neural networks, and they're pretty useful for text and other kinds of things that have a time-dependent data. So that's a good question. Axis 1, axis 0 is just a construct in the pandas toolset where axis 1 means, for our case, it was y-axis, and axis 0 means x-axis. So if you see a matrix which is rows and columns, so 1 is then columns and axis 0 is rows. So it's just a toolkit thing. So another good question about transformation for normalizing the training data on the set. So that's a great question. So you should always, in practice, kind of normalize entire data set and then partition it. But for our case, it was okay to normalize it because the data was random enough so that we could do it. Next question, if in our classification, if we just remove the entries with species 0, because it was very obvious that species 0 is easily clustered around sepal width of 2 or something. So yes, so that would have been an easy thing to do. And so this is something that you look at the data and you can do that easily. And in terms of performance, things would get better because then you have to classify only 2 items and the third is automatically classified for you. And that's a possibility. Next question, if the confusion matrix that is generated, is it the actual confusion matrix that we want? So confusion matrix is basically a plot of actual values versus predicted values and how many of those were predicted correctly. So if you look at the diagonal of the confusion matrix, that's where you want all your entries to be. So anything outside of the diagonals, one of the diagonals, which is the leading diagonal, if you have anything outside of that, they are not the same as the ground truth. So that's what you want. So if you look, that's the reason we have confusion matrices. It can tell us at one glance, like how many of the items that you predicted are correctly classified. What is accuracy? So accuracy is a metric when you do the fitting. You can have a loss and you can also have a metric to go along. So accuracy metric basically is number of things that were predicted accurately. So that's the average of that. It gives you a percentage essentially. Then somebody else had like, they tried training with 20 epochs and made the confusion matrix perfect. But in the plot loss, validation loss was higher. So that's basically means that you have overtrained. So if your confusion matrix is perfect, but that's like if you do it for prediction, then that's a good thing. So validation loss can be a little bit higher than the training loss. That's okay, but you don't want it to be too far away from it. So usually it's a bad sign if it's too far away, but if it's close enough, then you're okay. So how do you detect overtraining? So you, again, the same as the last question, if your validation loss is very different from your training loss, or different in the sense that it's the accuracy is less, then you have overtrained essentially. So the error can keep going down, and that's okay. It is the validation loss that is what will tell you if you have overtrained or not. So I'm getting this question every single time, like where can I find instructions to set up the Colab environment? So that should be clear by now, hopefully. And if it is still not, then just send out a note to the moderators. They'll tell you. So it's essentially you just go to the shared Google Drive, open up the Colab notebook, and then it will ask you if you want to hook up this Colab app to your notebook. And from then on, it should be fairly obvious. Or just go to research.colab.google, and then it should be easily accessible from there as well. All right, so now we've answered the questions. Let's see what where we left off last time. So I'm going to go back to the slide deck number 3, and we'll pick up back up from the normal distribution that we were talking about. So the reason I'm covering this in much detail is because I want to get away from the basic regression that I described first as the minimization of the sum of squares, and we want to get into talking in terms of distribution. So the normal distribution I described to you as that if the samples are independently and identically distributed, then they fall into this kind of a normal distribution. Examples are height of people. It's normally distributed. You'll have some average height, and then as you get away from the average, you'll get more and more rare events. There are people who are 2 feet tall on this side, people who are 7 feet and plus tall on this other side, and the average is somewhere here. So a lot of things are distributed normally like that, and we give example of a factory where you are manufacturing nails, where you want to manufacture nails that are 2 inches long, but as you measure them for quality control, you will find that most nails are a little bit around 2 inches, and once in a while something bad will happen with your cutting process or measuring process that you will find like a 1-inch nail or a 5-inch nail on this side. So that's how they are normally distributed as well. And what's good about the distribution that is normal is that you can describe it with just 2 numbers. One is the mean, and the second one is the variance. So mean is the item that is right in the middle, and the variance is how fat this curve is and how it slopes. So that's essentially how you describe a normal distribution, just by these 2 numbers. And this scary looking function basically gives you a probability that given any number x with a distribution mu and sigma square, what is the probability that that sample belongs in this distribution. So as you can see, when x equals mean, this all becomes 0, this becomes 1, and that number is the one that you will have for the probability, which is always going to be in the center. So at mean is when you have the highest probability. And because these are discrete events, if you sum them all up, they should all add up to 1. So that's another good property that we know. So how does that relate to what we are doing, or why am I talking about all this so much? So let's go back to our regression that we did. So we did plot a line that tried to fit our data points. So the actual data points are in red here, and we came up with a regression line that gave us these points on the line. So from this point that we came up, if you draw a vertical line to the actual point, and that green line is what your error is. So what we said was we sum up all these squares of all these errors and then minimize that, and that will give you basically the lowest cost, or the cost function that you then minimize. So what is happening here, that if you imagine our example of the nails, so each of these points are themselves coming from some distribution. So if, for example, this y is 6, so we say this is a 6-inch nail, then it is basically coming from all the nails that are kind of like 6.1, 5.8. So all these, this one sample represents a distribution that that this particular sample is coming from. So what we can think of then is that each of these things is itself a distribution. So what we came up with, if this was, this line actually went through the points, then our point that we came up with would have the maximum probability of being in this distribution. So it would be right at the mean of this distribution. So all these points that we came up with, they would be at the mean or the maximum probability. So if we turn this graph around and we look at that, so our predicted point and the actual point, if they are farther apart, then the actual point's probability is lower than the predicted probability. So ideal case, this red dotted line would be the same as the blue dotted line, and you would have a perfect prediction. So that's essentially what we're trying to do, is trying to maximize this probability, or maximize the likelihood that the point that we are predicting, it comes from this distribution and is maximized. So that's the intuition behind the distribution and the maximum likelihood. And we can look at it mathematically. So if, again, don't worry about this complicated math here. I just want to give you an intuition of what it is and why it comes to be like that. So just follow along here. So this particular function that we said about normal distribution says that given a sample X with a distribution mu and sigma square, this is the probability that it belongs to that distribution. So that is for one sample. So if you have a lot of samples, you would have conditional probability, which is basically a multiplication of all possibilities for all the samples. So this big symbol here for product essentially is saying that for all the samples X, the probability, the conditional probability is then the product of all these probabilities. So we basically keep multiplying this, and you end up with this equation. So now what we're saying is that we want to maximize this probability. So to maximize this particular function is complicated because it's an exponential and it's a product of many such things. So what we are doing instead is going to take log on both sides. So when you take a log of an exponential function, the exponential part goes away, and then you can reformulate this to look something like this. It's basic algebra. You can try it out when you have time. So essentially what we've done is taken log on both sides. So then when you take log of a product of things, it becomes a sum. So this is where it, you come to that, and then this exponential essentially goes away. So you end up with this. So this is a log likelihood of probabilities. And then if you look at this particular expression, it is exactly the same as the sum of least squares. So because we are trying to get to the mean, so this becomes the predicted point. So you're essentially summing up all the squares and then trying to maximize this particular equation. Because there is a negative sign, you're essentially minimizing this particular part of the equation. So maximizing the log likelihood is exactly the same as minimizing the sum of least squares. So that's the result that I want you to take away from this, is that the sum of least squares is a consequence of these distributions and probabilities, and that's where the log likelihood comes from. So this is the most math we are going to cover in this course. So far, I hope this is clear. So somebody had asked a question, clarify what is the difference between MLE and MSE. So it's essentially the same for a normal distribution. So that's what we just covered, that the maximum likelihood, which is the maximum of this expression, eventually turns out to be the same as minimizing the least squares. So I hope that is clear. And if you have any questions, we can go over it again in a later class or through question and answer sessions. I want you to think from now on in terms of distributions instead of sum of squares. Okay, so having said that, let's then get back to the actual networks and machine learning part. So today, then we are going to cover something called an autoencoder. So in our first regression problem that we solved, we had a network that looked something like this. So it's a fairly common network, simple input layer, 2 hidden layers, and an output layer. So what an autoencoder is just not a different kind of network, but just a rearrangement of this so that you have a structure that looks something like this. So it converges in the middle and then expands back. So it expands back to the same size as the input, and in the middle it's constricted. So this particular shape of the network is called an autoencoder network, and it has some nice properties. We don't use them directly, but it's also a stepping stone to understanding generative networks and variational autoencoder. So we're going to build this today and try to understand what it does. So as you can see, by doing this, you are going to constrict your network in a way. So for example, if you only have 2 nodes here in the middle, so by the time you reach here, you are taking all of your data and representing it with basically 2 variables. And that is what causes the compression or the encoding. And from here on, then you can start expanding and you can reconstruct or try to reconstruct the original data set by going back up to the full size as the input. So that's the entire purpose of an autoencoder, is to figure out some encoding, like 2 parameters here that you can compress your data to. So imagine if you had your housing data with 8 parameters, and it was things like number of bedrooms, population, zip code, and all those things, and they get compressed to just 2 variables. And we don't know what those variables are. They are in some hidden dimension, some latent space. So we say we can call them A and B. So all of those 8 parameters, sorry, got compressed to just 2 parameters. So imagine taking a 3-dimensional something and then compressing it to a 2-dimensional image. So that's a similar process that happens where you are essentially encoding the data into a different space. And then from there, you can then expand it back to the original data. And then because there is some information loss, because everything cannot be represented by a compressed data space, when you reconstruct it, there will be some difference between the original and the input. So you will have some loss. So if you look at it as a function, then it looks something like this. So forget about the networks. If you think of encoder as a function and the decoder as another function, then you're taking some input, which is X, you're encoding it. And once you encode it, you get a different representation. And you can then take that and decode it, and you get some output O. So ideally, O and X should be exactly the same, but in practice, they cannot be because of this compression that happens. So it would be close enough, depending upon the network size and how much this compression is happening. And this doesn't have to be 2. This can be 5, for example. So you're going from 8 to 5. So there will be less compression, but also you would have more chances that the input is very similar to the output. So that's the idea behind autoencoders. So let's look at some questions. So somebody asked, is this similar to PCA? So yes, it's very similar to PCA. So PCA is something called a principal component analysis. And it's a similar thing that we are doing here. Another question from Andrew Christensen is, are the latent parameters subset of the input parameters? So that's a good question. So they're not. So they are something in a latent space. So we don't know what that space is. And they can be, and usually are, very different from the input parameters. So they may not make sense at all. You can't plot them sometimes. They may not even represent images. So if you have 4 as an image here and you compress it, it may just be some numbers and that you can't make sense of it, but you know that your data has been compressed down and you can use that encoding to decompress or reconstruct the output. So another question is, can you quantify the loss in a mathematical formulation? So yes, we can. So if you have images, you can easily see the loss by just doing a difference of pixels. So that's one easy way to do the losses. So that's a simple mean average error. You can also do squared error. So you can use all kinds of metrics and errors that we talked about in trying to quantify this loss. All right, so moving ahead, let's build an autoencoder. We'll do exactly this. We'll predict, we'll encode the digit into some latent representation and try to decode it back. So let's look at this file, autoencoder.ipynb. So now we're going to be dealing with the images. Okay. So we're doing the same thing, importing some packages that we need. All right, so this particular data set is called mnist. It's a classic data set that everybody uses to learn machine learning, so we're going to do that too. It is available through TensorFlow as a data set, so we don't have to do a lot of software stuff to get this data. So what this data contains is a grayscale images of handwritten digits. And it is small in size, so it's only 28 by 28 size of images. So we're going to load this. So this is already kind of partitioned out in training and testing. So when we load this data, it already, you can assign it to different arrays. So that makes it easy. And these are grayscale images. So grayscale images, essentially the color ranges from 0 to 255, for 0 being black and 255 being white. So, and then all the values in between represent some gray value. And so 28 by 28 is the pixel size of each of those images. So let's normalize this. We'll divide it by 255, so then everything falls between 0 and 1. So right here, we are downloading our data set and then preparing it by separating it out into training and testing, and then normalizing it to be between 0 and 1. So let's look at what it looks like. So looks like there are 60,000 images, each of size 28 by 28, that is in the training set. And then in the testing set, you have 10,000 images. So we have enough data to train and test. So when we talk about images, they are two-dimensional arrays. So we are loading that as a 28 by 28 matrix that is 60,000 deep. So imagine this three-dimensional stack of images. Each image is 28 by 28, and then you have 60,000 such images. So this becomes a two-dimensional array. what we are going to do is going to treat each pixel as a feature. So now the number of features that are the input set, that is 28 times 28 or 784. So we have a lot of input parameters here. So um, in the flower data set, we had only 4. In the housing data set, we had only 8. But in this case, we have 28 times 28. We can treat each pixel as a parameter. So that's a pretty big sized input feature set. So let's print some of the digits and see what they say. So we are printing the shape of the training and the testing, that is 60,000 and 10,000. I'm going to take 10 items from the training set and the ground truth for those, and they are 5, 0, 4, 1, 9. So these are the labels for the data set. And we are not doing classification here, so you won't need the labels, but just to show you that there are labels in this data set, and these are the labels for the first 10 data elements. Okay, so next we're going to just plot some of these. So we take these 10 things, and there's an easy method called IMShow that is going to plot these as images. So it understands the sizes. All you have to do is give it the data, and it will plot it. And because we are using grayscale images, we're going to use a gray color map to plot these. So this should plot you 10 images. And there they are. So they're scaled up, so they look more jaggy than they are already. So this is 28 pixels here, 28 pixels this way. And so this is 1, 3. There should be 10 of these. There. So that's how you look at the data set as images. So remember, in an array, usually in images, you go 0 to width here, 0 to height here. But in case of matrices, you go 0 is at the top left. So you're going this way and this way. So rows and columns. So this is a square image, so we don't worry too much about which dimension is which, but in practice, things will not be square. So you may have to be careful whether you're going from 0 is here or 0 is here. So some operations on images, you may want to be careful because the matrix orientation is not same as the Cartesian coordinate orientation. All right, so now we have plotted the images. We know what they look like. So they're handwritten digits, lots of them. So next, we are going to build our autoencoder. So this thing should not look any different to you than the other one, except we are kind of shaping the network in a way where there is constriction in the middle. So what we do is we take the input layer, 28 by 28, we're going to flatten it so that it goes in as this one long list of numbers. So one long list of 28 times 28 is 784 numbers. That is our input feature set. And we're not going to have any intermediate layers. We're going to immediately compress it down to 32 nodes from 784 to 32. And then immediately expand it back to 784. So that's our simple model for autoencoder. And once you get the output, you're going to get a long list of 784 numbers. We're going to reshape it back into a matrix form that we can display as images. So that's all you need to build an autoencoder. So let's build that and print the summary of this. So as you can see, you got input as 784 after flattening, and you had one dense layer that is compressing it down to 32, and we expand it back to 784 and reshape it back into the shape of an image we want. So as you can see, the number of parameters is huge. So we have about 51,000 parameters here, and So that is a consequence of images. So images will explode the dimension of your network significantly, and that's something to worry about. And imagine if you had like an image that was 500 times 500. So 500 times 500 images, if it's a grayscale, then you have only one parameter per pixel. And that, if you connect it to a 32 node network plus the bias, you will end up with these many parameters. So that's huge, and that's going to be cumbersome. That's just in this layer, and the next layer will have even slightly more. So now imagine if this was a color image, then you'll have 3 numbers per pixel, and that would be even more. So this is something known as the curse of dimensionality, where the bigger the things are, the larger the network, larger the memory you need, more computing power you need. So everything we do is mostly about managing that complexity. So because this is a fully connected network, everything is connected to everything, that is the main cause of this curse of dimensionality. So all the other kinds of network that we have come up with, despite having different properties, the main function they provide is the sparsity of the network, so that you don't have as many nodes as you need. There are other techniques people use to curtail the size of the network, but having a densely connected network with such large number of inputs is untractable. So that's why you have something like CNN or other networks that can take care of reducing this dimensionality a bit. Okay, everything is good so far. So let's build our model. So it's good to create functions like this, so you can try out different models in different functions and then use any one of them. So we're going to call this, use this model and compile it. And now we're going to fit it. So fitting here is different than regression. We don't have a ground truth. Our ground truth is the same as our input. So what we are trying to do is reconstruct the input image. So we are going to train it against itself, essentially. So that's why we have in our Y input the same thing as X train. Okay, so hope this is clear. So because we don't have a ground truth. Our ground truth is the input, basically. So let's train it. So this is still fast. So many commercial networks will run for weeks, and we are still able to do this in a class. So I want to keep this as interactive as possible. So it's still going on. So looks like it trained, and then things to look for is the decrease in the loss, which is happening, and that's exactly what we want. So let's see how we did. So I wrote this plot function that shows you the results. All it does is essentially it plots 2 rows. In the first row is the original image, and the second row is the decoded image. So remember, this all thing has been trained, and you have encoded things, and then in the next step, you're going to decode it to go back to the original image. So this is where we do the prediction. So we take 10 images from the test data set, and we call predict on it. And so this particular function, again, don't worry about it. The predict function expects batches, and we don't have batches, so we do this something called expand dimensions, which will add a batch size to it, and it's just a quirk of TensorFlow, so I don't worry about it at this point. And we are going to create arrays, original and decoded. We're going to save this as original, and then we are going to take this predicted image and again remove the extra batch dimension by calling squeeze. So squeeze is the opposite of expand dimensions. Again, don't worry about these particular methods that you need to call in the API. So that's just imagine you just predicted and then you are saving it out. So now you have two arrays, original and decoded, that you do for all the 10 images. And then you call this show method, which is going to plot them in an array. So execute this. I should have run this. Okay, so there you go. So this was the original set of images, and this is what we decoded after compressing it down to a 32 parameter space. So it looks pretty good. As you can see, it's not going to be exact, and there is obvious issues with this number 9. You can see that some detail is missing from this number 9, but overall it looks pretty good. So imagine we've achieved a level of compression that is huge. So we went from a 784 size image to a 32 size space. So we achieved a compression factor of 24.5, which is huge. So we can do a few things to improve this. We can, as usual, let it run for more because it's still working. So let's keep running it. And again, when you run it without compiling your network again, it takes over from where you left off. So if you see the loss is already low and it's going to keep decreasing. So it should stabilize at some point. So if your loss is 0, you're kind of in trouble because which means you have memorize the data. So you don't want your loss to be exactly 0. You want it to be close enough so that you can see that. So now we have reduced the loss further, not a whole lot, but a little bit. So it should look a little bit better to you if we did that. So it does look a little bit better, but not a whole lot. So the reason it doesn't look much better is we are doing some extreme compression here. So if you look at normal compression libraries like JPEG or PNG, they don't achieve this level of compression. The level of compression is barely like, it's not 2x even. So we have compressed it to a factor of 24.5. So that's going to create some loss. So one thing we can try to do is not compress it so much. So maybe we just compress it down to 128 and see what happens here. So let's do that. Build the model again, use the model, compile it, train it. So now we're not compressing as much, so we should get better results. Although the network, as you can see, is running slower because now we have increased the number of nodes in our network by a lot, actually. So let's see what it was. So now we have 200,000 parameters. So another question is, where is the compression factor? So the compression factor comes from how many nodes you have in the latent representation, right? So that is how many parameters are in that. And because we're treating each pixel as a parameter, so if you think of it as an image, then the compression factor would be 784 times whatever node you have in your number of nodes you have in your latent representation. So in this case, it's 128 now. So we've reduced the compression factor down to 6. But as you can see, the quality will improve. So we trained it, took a little longer, but it looks like already the losses are better. Okay, so keep an eye on this bottom row. It should look better. There you go. So it already looks better. You're trying to now get some detail here on this 9, and that 4 is also much better. So there you go. So you cannot remanufacture the missing data, but you can come close enough if you allow for some decent compression still. And factor of 6 compression is extremely good. So it's nothing to laugh about. So there it is. You built your autoencoder, and it's something that will help us understand other things we are going to cover next time, basically trying to see what else we can do with an autoencoder. But so far so good. All right, so let's see, did that. So one thing you can do for your homework, because this particular data set also has the ground truth or the labels 0, 1, 2, 3, you can try to classify this. You can see you can try to see which digit belongs to or which number it is. And so there'll be 10 output classes in that case. So try that as a homework. What you will find is that it's able to classify things, but so this is an example of how neural networks learn and what where they can fail. So this number, somebody put a sticker on this, a black sticker next to the 3, so that it looks like that. To all human beings, this looks still like a 35, but to a neural network, this would look like an 8, because it's more like an 8 than a 3 to a neural network. So it would try to classify it as an 8. And that's where, like, if you drive your Tesla and you have it set on autopilot, is going to speed through this area at 85 miles per hour. So it's very clever, the neural networks, but it can be fooled in simple ways. That's one thing to know from that. Robots are not going to take over your job anytime soon. So try to see if you can classify different digits, and we'll see. So one thing you can do, when you classify, you get these probabilities of things, right? So you can find the class with the highest probability. Say something looks like an 8, it would be classified as 8. It might have a probability of 0.7 or something. I also want you to find the next likely digit. It's like if something is an 8 with a high probability, but then what is the next lower probability? And it's most likely going to be 3 for if something looks like an 8. So that would be a good thing to show, like what the neural network thinks the digit might be. So try to do this as a homework, and if you have questions, let me know. So the data should have everything that you need. If not, like if when we covered it here, this is the label for each of the data points. So you can use that as the ground truth and then do the classification like we did. So you'll make a classification network where you will have 10 output nodes and each one representing a digit. All right. So next stuff, what do we do next? So we built an autoencoder already. So next thing we're going to do is try to figure out, like, we had a small data set, 60,000 images, very small size, 28 by 28. Then in practice, you're going to be dealing with very large images. Now, how do we do that? And so one application we're going to try is something called denoising. So given a noisy image, how can you get something like this? So this is from an actual paper that we wrote in 2018 about denoising ray traced images. And it works pretty well. you can take something like this, pretty grainy, and then get a nice clean image that looks like this. So obviously you need to train it, you need ground truth, but it should work. So before we can do that, because these are large images and color images, we will need to figure out how to do that. So the idea is that when you look at a distribution, you think of images in the distribution. So if you think of a clean image as the mean of your distribution, and then the noisy images are surrounding images in that distribution. So if you look at the whole spectrum of your distribution, it may be noisy image and clean image. So essentially what you're trying to do is find a clean image from that distribution. So if, again, this helps when you think in terms of distribution where all images are there in this distribution and they're in some way accessible to you and you just have to find it. So we'll do that. And the thing is, like in ray tracing, you have easy access to noisy images. So usually when you deal with random images, where do you get the noisy version? All you have is usually clean image, or all you have is a noisy image. So what we can do is we can take clean images and we can add some noise to it for the purpose of training. And this process is called data augmentation. It's pretty common. And we can create new data for training purposes by adding a noise that you would encounter in real life as well. So we need to create more efficient pipeline. So we will do that next. Let's go to this data pipeline.ipynb file, if you can find it. I can't find it. Okay, let me go check on this file quickly. So in the meantime, if you have any questions, just post them. Where did it go? Okay, so I found it. Now. Okay, so this is the file. It's called datapipeline.ipynb. Again, we do something similar, load some packages. So in this particular case, we are going to be dealing with something called TensorFlow datasets. And this is available from the TensorFlow library itself. It's called the UC Merced dataset, and we are going to download it. It's a little bit large dataset. So we will let it download as we speak. It's about 300 megabytes of data. It's going to download it, and let's let it go ahead. And so TensorFlow dataset is a construct inside of TensorFlow. It's called TFDS, and it helps you create very efficient pipelines for data. And we'll cover some of that today. And then when we do CNN or convolutional neural network next time, we will go into detail of this. But I want you to have this file so you can read it and try to understand as much as you can from it. I don't expect you to fully kind of figure this out, but then I'll help you do that next time. What it does is it basically takes the data set. Let's see if it's still loading. Looks like it's still loading. So don't worry about these functions for now. So because you want your data to be as efficient as possible, these structures, they're not using Python. So in Python, looping and other things can make things slower. So this is using the TensorFlow API to perform all kinds of operations on the data directly. So try not to call native Python functions directly when dealing with the TensorFlow dataset, because that will only slow things down. So if you look at that, everything I'm calling here is directly related to the dataset. And this map is not the Python map, but it's a TensorFlow map function. So that keeps things efficient. Again, I don't want to go into the detail of this today, but just want you to see what is happening. When you load a huge amount of data, it does take time. Looks like it's loaded up now. So, okay, so this is the information about the data. These are set of satellite images. There are 21 classes in, so we have some ground truth here. There are images. So because we are creating pipelines, we don't specify normally image sizes directly because we can deal with any image size. All this tells us is they are color images because of this 3 over here, R, G, and B. And it's got another parameter called file name. So we have 3 parameters per data point: file name, image itself, and the label. And there are 2,100 images in here. And we have no real split here. It's only a training data set for 2,100. We have to split it ourselves. So we can do classification if we wanted to with these 21 classes, but that's not what we're going to do here today. So this is all the details about the data. Each size is 256 by 256. So these are large images comparatively compared to the mnist data set, which was 28 by 28 by 1. And these are 256 by 256 by 3. So let's look at the image types. They are unsigned integers. Each of them is an R, G, and B. Like each image has pixels. Each pixel has color, and each color has a number, which is an R, G, and B. Each is an integer. So then we can get this as a TensorFlow data set, and this particular thing will show some examples from the data set. And we can see 9 images. These are high quality satellite images, and image itself, the file name here, and the class that it belongs to. So there are 21 classes, as we said. We're not going to deal with that, but just to know what this data represents. So I'm going to stop here. And next time when we build the convolutional neural network, we will reuse this part and then we'll add the network part. But take a look at that if you can try to understand what we are doing here. We are transforming the data in some way using these 2 functions called extract patches and add noise, and see if you can try to understand that. It's not a homework, but just as something additional. So for the homework, try to see if you can classify the mnist data set, and then for extra credit, which I don't know what this means, show the next likely class that your data belongs to as well. So that's all I had for today. Let's see if we have in a couple of minutes can answer any other questions. Okay, so looks like things are good. So somebody had a question about, like, if you are coming from a ray tracer, then you can generate a less noisy image by using more rays. So that is definitely possible. And in fact, that is exactly what we're trying to avoid. So tracing more rays takes time. If you look at a professional renderer in a VFX or an animation setting, a good, decent render can take up to 8 to 9 hours. And by denoising it earlier, so you can save some hours. If you can train your network and the ultimate prediction part takes only like 10 seconds or 20 seconds, then you can save a lot of time by, because most of the noise that remains, it is very hard to remove in ray tracing, and then you can probably render for days and still not reduce it fully. All right, so any other questions you have, please follow up on Twitter or connect with me on LinkedIn or other places. I'm available everywhere except Facebook, so whatever you want to connect with me, it's okay. And I will see you next time. Thank you, everyone.